So third order difference equation, so we'll start with yt. That is going to depend on phi1 yt minus 1, phi2 yt minus 2, phi3 yt minus 3, yes, plus that wt part, right? The white noise component. You should know what the characteristic polynomial is. I'll give you a minute or so. Let's see if you can write the characteristic polynomial for that difference equation. Similar to one of the other problems. So we want to keep Wt on the right hand side. So yt would be equal to phi1 lag operator yt, phi2 L squared yt, phi3 L cubed yt plus wt. Good. Going to move everything to this side. So yt minus phi1 L yt, phi2 L squared yt, phi3 L cubed yt equals wt. What do I have in common? Yt. How do we get the characteristic polynomial, which is phi of z? Replace the lag operator by z. And this is the noise part. Independent, identically distributed, typically Gaussian noise. Good. So phi of z would be 1 minus phi1 z, phi2 z squared, phi3 z cubed. We're done. Characteristic polynomial. And if they want to express this in terms of C's and size, we've got to set this equal to 0 and find the roots. How many roots would we have? 3, because this is a third order polynomial or third degree polynomial. So uppercase. Based on our knowledge from the previous case, second order difference equation, what would lambda 1, lambda 2, lambda 3 be?
1 over Z1, 1 over Z2, 1 over Z3.
I keep using model, we'll get to that later, difference equation. Correct. I also mentioned that we can get this from using the eigenvalues of a matrix, correct? Last time we had one, we're going to have one this time also. So the lambdas what was it for the last one? I think it's just P1, P2, P3, my bad. P1, P2, P3. 1, 0, 0, 1. And 0, 0. Good. We can extend this model over and over. And so the eigenvalues of this model will give us lambda 1, lambda 2, lambda 3. Of course, we can't use the calculator. I'll give you the eigenvalues if it's a homework or a big time. Clear so far? Great. That's a third order polynomial. And that's going to be hard. We know how to solve a second degree polynomial without an equation. Great. Third degree polynomial, we can solve and find the roots if you can factor it. Great. We can't always factor. It's not that easy. Imagine if we had a fourth order difference equation. We have 4 factors. You really want to do that? Of course, there are simpler cases where you can, but there are cases where you simply cannot. So we did a shortcut to get to those roots. Instead of finding the Z1, Z2, and Z3, we found the lambdas. And I, gave you that shortcut. Can I erase this? To solve phi, uppercase phi of Z, we use, what did we use last time? Oh, use in the sense I expressed phi of Z in a specific form. I wrote it in a certain way. Right before that step, before the partial fraction step, I took that polynomial and I wrote it in a certain way.
You wrote it 1 minus lambda 1 Z times 1 minus lambda 2 Z. Because I'm assuming we have a 1 minus lambda 3 Z.
Right? That is the factor form. So if we know the lambdas, then we would be able to to come up with the roots easily. And lambdas are simply the eigenvalues of that matrix. Easy to find those also. What was the next step? Our next step is to recognize that the weighted point. Our objective is to divide by phi of z. So we will have 1 over phi of z. And what would phi of z end up being?
The 1 minus 1.
It's your one, it's your factor.
What did we call this? Yes, but we call this something. Sine. Sine. So that entire thing is sine z of W2. But what is psi z? Psi z is 1 over 1 minus lambda 1z, 1 minus lambda 2z, 1 minus lambda 3z multiplied together. Good. In order for us to write yt in terms of wt, we had to split this up. Correct? How did we split it up last time? Partial fractions. So what I'm going to do is split this up using 3 constants. Last time we had 2, now we have 3. Good. So if I find C1, C2, C3, then I could do what I did earlier today and write yt in terms of wt's. Yes? No? We can. So the objective here is to find C1, C2, C3. Pretty straightforward, right? We'll do it next time because it's going to take a long time. But the moment we do it, you will see a pattern for C1, C2, and C3. And that pattern is very nice. So once you recognize that pattern, I can apply it for any P. And all CPs will follow the same thing. And if we can do that, then the dynamic multipliers, in other words, how tomorrow will be affected based on what happened at time t, can be easily modeled using CP. That makes sense? Yes. Good place to stop. We will derive values for C1, C2, C3, and do an example, and that will be the last point. For the first example, I am going to release the next homework, which will have this, but we will just wait to do it.